Morning, fellas. I wanted to go over some sampling distribution uh, examples. All right? And this is, you guys had a lot of good questions on the discussion board. It seemed like there's a lot of questions about central limit theorem and some of these normality rules for proportions and our standard deviation recipe and requirement of having 10 times the sample size, of the population being at least 10 times the sample size. So, in honor of Eamon Coffey, I have a population here. This is made up. It would be this is the population of SAT scores of incoming freshmen at BC. And you can see the shape of the distribution is pretty skewed right? It's centered around 1292, standard deviation just under 80. So clearly a non-normal population. Just of note, if our population is normal, then regardless of the sample size, the sampling distribution for mean, this is all, we're dealing with mean for all of these problems, the sampling distribution will definitely be normal regardless of the sample size. Now, I want to consider samples of, say, 5, 15, and 30. Now, to figure out how many samples there are in that sampling distribution, I'd have to use that binomial coefficient, the combination function, and it's a massive number. So I can't possibly list all of them. So instead, I'm going to take about 2,500 of them, which is a lot, and it'll give us a pretty good picture. So this first graph is just a smaller version of what you saw on the previous page. All right, so again, we can see it's skewed right. We can see that the population mean, we'd call that mu, is 1293. The standard deviation is 79.54. Now, if I take samples of size 5, and I took 2,500 of them, the mean of those means, right, mu sub x bar, the mean of all of those sample means, is pretty darn close to 1293. And that's not surprising because x bar is an unbiased estimator. If I took every possible sample, so that would be 2,500 choose 5, which is a massive number, it would be exactly equal to 1293. Right? So we can see, even with pretty small sample size 5, our sampling distribution is close to normal. A little bit of right skew still remains. The standard deviation of this sampling distribution has gone down a lot, right? We've pinched the ends in a little bit. It's decreased to 34.88, pretty darn close to the standard deviation of the population divided by the square root of 5. Right? So even though we don't have the full sampling distribution, we're seeing that as sample size increases, standard deviation of sampling distribution decreases. Right now I've taken samples of size 15. Right? This is getting very, very normal. Right? Again, the population standard deviation, so they should say, population standard deviation is just under 80. The standard deviation of the sampling distribution has decreased even more because our n has gotten larger. So we're dividing by the square root of n. That sampling distribution standard deviation is dropping, and we're getting closer and closer to normal. So a lot of people ask the question, why 30? It's just a rule of thumb. It's just the experience of statisticians in the past. They've seen that as we get closer to 30, regardless of the shape of your original population, your sampling distribution is going to get pretty normal. We can see here that it got pretty normal fast because the population was not too far off from normal. So, I mean, it is a balancing act of how close is your population to normal. You can get away with a little bit smaller sample size. But we just use, as a rule of thumb, 30. And you'll see in later chapters when we start to deal with t-distributions, which are close to normal but not exactly normal, we can get away with even smaller sample sizes. But for now, if we don't know that the population is approximately normal, we have to just default to the central limit theorem and say, all right, the sample size has to be 30. I've got an applet here, and I'm going to put a link on Blackbaud to this applet. And this is interesting. We can play around with this. If we want to change this parent population, let's try to make something that's pretty skewed. And then maybe I generate 100,000 samples of size 5. And how about I throw a normal curve over that? So you can see how it's not too far off. We can look at the mean and the standard deviation. I can maybe do a larger sample size. Oops, I don't want to animate that. I'd rather just see 100,000 of them. And we can see how we get closer and closer to normal as sample size increases. So you can play around with this to get an idea of how these things change, how the mean, notice the means are the same every time, 9.43 in this case, and the standard deviations decrease as your sample size increases. So if you want to play around and try to prove by example how standard deviation is affected by sample size, you can feel free to do that, and how shape of sampling distribution approaches normality, you can play around with that. There's another one, it's a little bit better applet, another one for proportions. Okay, so just going to jump to another screen. Remember, for sample means, so we're talking about x bars. The mean of all the x bars is equal to the mean of the population. The standard deviation of all possible x bars is equal to the standard deviation of the population divided by the square root of n. And the shape is normal if the population is normal, which it sometimes is, or if we invoke the central limit theorem, because the sample size, sorry, a little pen difficulty, is at least 30, then we can say it's normal. Also of note, because we're sampling without replacement, we need, sorry about that, we need the population to be at least 10 times the sample size. Now when we're dealing with proportions, so sample proportions, there's all these p hats, in the mean of all the sample proportions is equal to the population proportion. The standard deviation of all the sample proportions is equal to radical pq over n, where q is 1 minus p. And again, we're sampling without replacement. Remember, our rules for a binomial setting is that the probability of success has to be the same every time, but we said we could violate that a little bit if we were choosing from a really large population, so pulling one individual out of that population doesn't affect P all that much. So N has to be at least 10 times little n. The population has to be at least 10 times the sample size. The shape is going to be normal if the same conditions exist as do for the normal approximation of a binomial distribution. In other words, NP has to be at least 10 and NQ has to be at least 10. So really want to be careful that we don't confuse the conditions for proportions with the conditions for means. Means, central limit theorem, n equals 30, or the population is normally distributed. Proportions, NP greater than or equal to 10, NQ greater than or equal to 10. It's probably the biggest mistake students make on this section, this chapter, is they confuse the conditions for normality. So I want to go back to this applet. Again, you can play around with this. We can look and see, okay, if the population proportion is really close to 50%, then we can get away with pretty small sample sizes and it'll be approximately normal. As that population proportion gets farther away from 50%, we get skew, right? If it's closer to 1, you're going to get left skew. If it's closer to 0, you're going to get right skew. So you can play around changing the proportions for given sample sizes. Now I'll try a bigger sample size. I'm going to reset to proportion 50%, sample size. Let's try 20. Right. Pretty close to normal, but you can see some gaps in here. We'll do another one. Reset it. Now if I increase the sample size, you can see it's really close to normal. I'm going to try a really small proportion. You can see it's pretty skewed right. Increase the sample size. Still pretty skewed right. Increase the sample size. It's getting a little bit less skewed. And less so. So it's a combination, right? A combination of sample size and population proportion that gets us this normally distributed sampling distribution. Right? Maybe I'll be a little less extreme. So you can see, even though our population proportion is really small, because our sample size is so large, we get something that looks approximately normal. If the sample size were small, not too normal. So just notice I'm increasing sample size as I go here, and I'm watching how this is getting more and more normal. Right? Because 1% of 10,000 is pretty darn close to 10. Right? So play around with that, and hopefully it will help you understand the effect of sample size on sampling distribution, shape of sampling distribution. So good luck with that. I hope to see you guys Friday or Monday, depending on which day our class meets. So have a good day.